Thanks a lot for the introduction, and welcome everyone in the audience. As you may have seen from my title already, I'm working with apples. And one nice thing about apples is, even though probably most of you haven't studied them professionally, most of you have at least eaten an apple. So if you maybe at some point had an apple that just looked fine from the outside, but then you took a bite and you just had this really bad taste, well, then there's a good chance that that apple actually had internal browning, because that's quite a commonly occurring disorder in apples. And it occurs after apples have been in storage for a long time, and actually most apples are stored for a long time. And if you cut the apple open, you can very clearly see all these brown areas. But to test if it's brown without cutting the apple open is quite difficult. And this is something that companies would like to do, because actually the apples are sorted according to their quality and then sold in sort of the most appropriate use. Well, my PhD is, can we use X-ray imaging to detect internal disorders in food? And for this project and the following project that I'm working on now, I've been looking at internal browning in apples. And so when we started the project, we collected a lot of CT scans of apples, but it's quite hard to judge what exactly we're looking at. So as you can see now, this is a CT scan slice of an apple, but it's not that clear what's really happening here. So it is quite a lot nicer if you have a photograph next to it, because now you can see, oh, hey, this is an apple with browning, and these brown spots that you see here correspond with the dark spots on the CT scan. So I set out to make a data set like this of photographs and CT slices. And to make this data set, I made use of image registration. What image registration is was already explained 2 talks ago by Ben. This is the first work on photograph image registration of fruit slices, although there are some similarities to histology image registration. And there are a couple of things that make this a difficult problem to work on. First of all, you're working with 2 different modalities. So photographs are RGB color and CT scans are grayscale. CT scans are 3D and photographs are just 2D. So there are many ways a slice could be oriented in the volume. There are not that many features inside the apple. The core of the apple is quite clear, but for the rest, the region is relatively uniform, and where you can see things, they're not that easy to match between the photograph and the CT. But you do have the outer shape of the apple, but even that can be hard to distinguish on photographs, because this photograph shows an apple where only a small part has been cut off from the top, but because the peel is also quite yellow, it can be quite tricky to distinguish where does the peel end and the inside begin. So to still work with these difficulties, I developed the following workflow. So there's 4 steps, and in the remainder of the presentation, I will go briefly into each of these steps. The first step is data acquisition. It's basically 3 steps. For in every apple, we drew a line to use as like a reference point to initialize the registration later. Then we CT scan the apple at the CT scanner that we have at the group, and we always sort of put the line in front, so there's a bit of like a reference position. And then we slice and photograph the apple, and for that we use the setup that's shown here on the slice. The idea is that we kept the apple in place with a suction cup, and it's pressed against this clear surface, and there's a camera that can take pictures of the apple through the surface, and by moving the apple to the side, one slice is removed. So just remove slice, take a picture, remove slice, take a picture, and that way you get like a nice data set of slice photographs. And these photographs will not have relative rotation, and the slice spacing will be constant. We did this for more than 1,000 photographs of more than 100 apples. And these data sets look like this. For each apple, we got about 10 usable images on the end of the Apple, usually some parts started breaking off, so these were excluded for the image registration. So moving on to the next step, I don't want to go too deep into this because I want to have some time for the other subjects, but for the photo, we tried to segment only the part that was cut, so not the peel. And to do that, we used the deep learning-based method. Segmenting the CT scans was a bit easier, so we could use a threshold-based segmentation method with some post-processing. And now we have both images in a view that is a bit more similar. And we use that in the next step, the image registration. Now, image registration, the point is always to, if you have a point on one of the images, you want to find the corresponding point in the other. So in this case, if you have a point in the photograph, you want to find the corresponding point in the volume of the CT scan. To sort of limit to really the degrees of freedom that are available in the dataset, I use this joint transformation model that describes the transformations of all the slices available for one apple. And most of the parameters in this model are shared. So the rotation, the scaling, the slice spacing, the z offsets, and the rotation parameters, they're all shared. Only the slices have separate parameters that allow them to be moved a bit like this, relative to each other. And to optimize this transformation model, I just took the mean squared error between the grayscale values, or at least the mask values actually. So for every pixel, the corresponding position in the CT scan was looked up, and I just took the mean squared error of that. And because I implemented this whole approach in PyTorch, you could then use the PyTorch gradient computations to do gradient descent on this data set. I used gradient descent of momentum to optimize this problem. Also because everything was in PyTorch, you could also run it on the GPU, which sped up the implementation quite a lot. And the nice thing about this joint approach that we sort of described all images in the same transformation model is that you're less sensitive to local minima. So after doing this, I got a data set like this. So I got lots of images, as I said, more than 1,000. And you can now visualize them that you have on one hand the photograph and then the registered CT slice. So this can really work as an atlas in a way to sort of say, okay, this kind of browning looks like this on CT. These are the top left one is a healthy apple, and the right bottom one is rot inside, and the other four are different types of browning. So that is quite useful for further research. And the rightmost column you can see sort of the registration overlay to get a bit of a qualitative view of the registration quality. But I also wanted to quantify it in some way. So I used the only feature that is clearly visible on both the CT scan and the photograph, and it's the core of the apple. And so first on the photographs, without looking at the CT scan, I annotated the core endpoints. And if I thought they may be hard to classify because either there wasn't a clear endpoint or the thing was pretty thin, I just didn't annotate it. And then later had the CT slice viewed side by side and annotated the corresponding points. And use that to take the average core endpoint error within this registration plane. And well, I tried it for different numbers of slices. So of course I had all slices available, but you could take a subset. So either only like this core slice or one next to it or the two next to it, or so up to 6. And you can see the more slices you include, the better the registration quality gets. So this joint approach was indeed working. And even in some apples, the registration error without doing this joint approach was so big that you couldn't really find the nice corresponding points of the core. Well, this brings me to the conclusions of this presentation. And it's first of all, it is possible to do image registration between slice photographs and CT scans of apples. And the registration error in my experiments was about 1.5 millimeters. Well, this data set will become publicly available. So this is a nice data set for further biological research. And as a bit more general solutions, well, if you can do joint optimization in your registration problem, it may benefit the registration quality. Secondly, PyTorch is really flexible, so it can be done to optimize a lot of things and run a lot of things on the GPU, which is very helpful. And yeah, so if you try to bring some kind of existing methodology to a new field, you will always run into practical problems, but it's also an opportunity to come up with creative solutions to fix them. So yeah, I've written a paper about this, which at the moment is still in review, but if people want to have a look already, I put it in archive. And also, I'd like to thank my co-authors for working on this with me. So yeah, that's the end of my presentation. Are there any questions?